Hi everybody, this is the lecture on section 6.4. So, section 6.4 starts out with yet another Taylor series. It's kind of an important one because it allows us to deal with square roots and cube roots and the like. It's called the binomial series, and it goes like this. So consider this function 1 plus x to the r. R is any real number, non-zero real number. Typically not an integer. Non-zero real number, typically not an integer. Okay. So let's take derivatives. Okay, we're going to find the Maclaurin series for this, the power series centered around 0. So the zero derivative, the original function, 1 plus x to the r. First derivative, r times 1 plus x to the r minus 1. You don't have to worry about multiplying by anything in the chain rule because the derivative of the inner function here is just 1. Second derivative, r times r minus 1, 1 plus x to the r minus 2, r times r minus 1 times r minus 2, 1 plus x to the r minus 3, so on and so forth. The nth derivative is r times r minus 1, r minus 2, all the way down to r minus n plus 1. Right, that's for the nth derivative. Third derivative has r minus 2. So this is r minus n plus 1. And then this is r minus n. Plugging in 0 for x, and taking the derivative at 0, you just, this 1 plus x to the exponent here just becomes 1 when x is 0, because it's 1 to some exponent, just 0. Or not 0, it's 1, sorry. When x is 0, 1 plus 0 is 1, so then this is just 1 to some exponent, which is just 1. So 0 derivative is 1. First derivative, r. Second, r times r minus 1. Third, r times r minus 1 times r minus 2. Nth derivative at 0, r times r minus 1 all the way down to r minus n plus 1. So now this thing here, this nth derivative, put it over n factorial like you're supposed to do with the Maclaurin series, and denote this fraction just by this notation. It's called r choose n. Okay, and therefore the Maclaurin series for f of x equal to 1 plus x to the r is sum n equals 0 to infinity, just r choose n x to the n. So it's just a compact notation. Right, so this series is called the binomial series. So n equals 0 to infinity, r choose n, x to the n, is called the binomial series. And it can be shown using Taylor's theorem that the function equals that. 1 plus x to the r is equal to the sum n equals 0 to infinity, r choose n, x to the n, for all x with absolute x less than 1. It takes a little bit of doing, but we're just going to go with that. Okay, just assume it's true. All right, so not to waste time on that sort of technical technical aspect of things. Okay, anyway, so let's just take a look at a basic example. How about just square root 1 plus x, right? That's 1 plus x to the 1/2. That's the sum n equals 0 to infinity. 1/2, choose n, x to the n. You know, which can be written without this notation. 1/2, choose n, as follows. All right, so for n equal to 0, 1/2, choose 0 is just, there's x to the n here. 1/2, choose 0 is 1. For n equal to 1, 1/2, choose 1 is just 1/2 times x plus the sum n equals, well, let's just keep writing it out. So next, it's for n equal to 2, 1/2 times minus 1/2 over 2 factorial x squared, plus 1/2 minus 1/2, 1 minus 1/3 over 3 factorial x to the third, plus 1/2 minus 1/2 minus 1/3 minus, oh, I'm sorry, not 1/3. Minus 1/2 minus 1 is minus 3/2. Then minus 3/2 minus 1 is minus 5/2 over 4 factorial x to the fourth. So on and so forth. So let's simplify this expression. So 1 plus 1/2 x minus 1 over 2 squared times 2 factorial. And then this one is going to be plus 1 times 3 over 2 to the third times 3 factorial. This one is going to be minus 1 times 3 times 5 over 2 to the fourth times 4 factorial. So on and so forth. Next term is going to be, so I'll show you what the next term is, 1, 3, 5, 7 over 2 to the fifth times 5 factorial. So, well, there's a nice pattern here, but the first two terms just don't fit it. So we'll just put those separately. Plus the sum, n equals 2 to infinity. Well, we have odd, this expansion of odd numbers. And then we have this positive, negative, positive, negative. So at 2, it's negative, 3 positive, 4 negative, 5 positive. So it's minus 1 to the n minus 1. So starting with the negative at 2. 1 times 3 times 5 all the way to, well, for the fifth term you got 7. For the fourth term you got 5. So that's the odd number, 2n minus 3. Over 2 to the n times n factorial. Oh, I lost my x to the n, didn't I? X squared x to the third. Did I forget that? X to the third minus this times x to the fourth plus this times x to the fifth minus, so on and so forth. All to x to the n. Right, x to the n. Right, so that's the expression. And notice it's an alternating series. So this is square root 1 plus x, square root 1 plus x, square root 1 plus x. Notice that this is an alternating series converging absolutely. Well, it's an alternating series for x larger than 1, converging absolutely for minus 1 less than x less than 1. But it does converge conditionally at x equal to 1. We still have convergence. And so square root of 2 is equal to this at x equal to 1. So it's 3/2. Right, when x is equal to 1, this is just 1, so it's 3/2 here, plus this alternating series. Right, and we know how to estimate alternating series. We know how to estimate the alternating sums. However, this series doesn't converge too quickly. Oh, there's just a 1 there. Does not converge. But let's check out a partial sum just to see how it goes. Let's check out one of the partial sums just to see how it goes. Let's check the written down here somewhere. Yeah, here it is. So let's check out the fourth partial sum. Or 4. No, the fifth partial sum. Let's check out is that the one I wanted to do? Well, let's see. It's not going to be too accurate, but we can do it anyway. So the fifth partial sum is 3/2 plus the sum n equals 2 to 5. So for n equals to 2, right, this is just 1, and then 2n minus 3 is 1. So that's 1 over 2 squared times 2 factorial is 8. And then that's a minus at 2. At 3, you're going to get 1 times 3 over 8 times 3 factorial is 48. And then for n equal to 4, For n equal to 4, you're going to get 1 times 3 times 5 over, so this is 32 times 120. 32 is 2 to the 5th, 120 is 5 factorial, plus the next one is 1 times 3 times 5. Well, that was the 5th partial sum. Let's do the 6th partial sum. Times 7. So that's 2 to the 6 is 64. And then 6 factorial is 720. Okay, so let's give that a quick calculation there. So we have 3 halves minus 1/8 plus 3 over 48 minus 15 over 32 times 120. Oops, 32 times 120 plus 15 times 7 is 105 divided by 64 times 720. And what do we get? 1.43872. All right, so and we know that the square root of 2 is 1.41 something something something. The first two decimal points are 4 and 1. So it's not too accurate. It doesn't converge very quickly. I mean, we didn't even, with the 7th or 6th partial sum there, we didn't even get 2 decimal places of accuracy. But, I mean, as you can see, it's approaching the right number. Okay? So that's nice. That's one example of a binomial series, and it gives you, this has this nice alternating quality to it. Okay, and as a matter of fact, it usually will when this is positive. So when this number here, when the x is positive, it's always going to have this alternating factor in it eventually, because whatever this number r is here, when you keep subtracting from r minus 1, r minus 2, r minus 3, all the way down to r minus n plus 1, eventually it becomes negative. And so it's a product of negative numbers, right? So eventually it does turn into an alternating series for positive values of x. Okay. Another example. How about just square root x itself? So find a power series representation for square root of x, and let's center it at a equal to 4. Okay? Well, square root of x is equal to square root of, well, it's 4 plus x minus 4 to the 1/2 power. Right? So I want to mold it into this form here. 1 plus x to some power. It doesn't have to be x anymore. So since we want to center it at 4, we're looking for that number there to be a 4, x minus 4. Right? So that's what I've got here. 4 plus x minus 4. Now I can factor out this 4, 1 plus x minus 4 over 4 to the 1/2. Right, this 4 becomes a 2 outside of that. And then we've got 1 plus x minus 4 over 4 to the 1/2 power. Right, so now I can apply the binomial series. It's 1 plus blank to the 1/2 power. Right, so 2 times 1 plus x minus 4 over 4 to the 1/2 is equal to 2 times the sum, n equals 0 to infinity. 1/2 choose in x minus 4 over 4 to the n. Right? Get that 4 outside of there. Sum n equals 0 to infinity. 1/2 choose n. So now I have 2 over 4 to the n, x minus 4 to the n. Right, which is going to be equal to sum n equals 0 to infinity, 1/2 choose n, and then this is 2 over 2 to the 2n, x minus 4 to the n. Right, and so now we have our final answer, n equals 0, 1/2 choose n, 1 over 2 to the 2n minus 1, x minus 4 to the n. For what? Anytime this thing is less than 1. For all right, so square root of x equals this. For all, x minus 4 over 4 less than 1. Right? In other words, for all x minus 4 less than 4. Right? So what interval does this give you? Well, this is the interval x minus 4 less than 4 bigger than minus 4. Right? So it's 0 less than x less than 8. So for all x between 0 and 8. Okay? So that just basic form for the binomial series centered at 0 can be modified in lots of very different ways to get power series expressions for all kinds of other functions, like just square root x centered at 4. So I need an x minus 4 in there, so I just write 4 plus x minus 4, and it should be a plus. Let me factor out a 4. Right, bring the 4 outside the square root, and now I have 1 plus blank to the 1/2 power. 1 plus blank to the 1/2 power, so that's already in the form for the binomial series, the regular binomial series, which is 1 plus x to the r. 1 plus x to the r is this sum r choose n x to the n for all x less than 1. So whatever x is, whatever blob you have in the place of x, well, you can just substitute that in. Right? So here I have 1 plus blob to the 1/2 power. So wherever the x to the n goes in the binomial series, I just put this blob right there, and then we just modify it so that it's just x minus the center to a power. Okay. So that's the binomial series, and that gives us a lot more power series representations for a lot of other different types of functions. So what do we know so far as power series go? Representations for a good many functions. And basic variations of this function, starting with this with these, starting with the power series shown in table this table here, right there, table 6.1. Alright, so we have 1 over 1 minus x, just basic geometric series, e to the x, sine x, cosine x, log 1 plus x, 1 plus x to the r, and arctangent. And now you can modify those in lots of ways to get a lot more different types of functions as power series. So, for example, so find a power series representation for cosine x squared and state its interval of convergence. Okay, so starting with table 6.1, cosine of x is equal to the sum n equals 0 to infinity minus 1 to the n minus 1 to the n over 2n factorial x to the 2n for all x. So, cosine x squared is the sum n equals 0 to infinity minus 1 to the n over 2n factorial x squared to the n for all x again. So now we would like to write it in the standard way, so it's a constant in terms of n times x to a power in terms of n. So you don't want to leave it like that. What you want to do is write it like this. X to the 2n. Alright, now consider this power, and that's for all x. Consider this representation, power series representation for cosine x squared. Okay? None of the integration techniques we have studied allow us to obtain the antiderivative of cosine x squared dx as a product, well, as an expressed using the usual types of functions. Usual types of functions. There's nothing in that whole section that allows you to solve this antiderivative problem. But we can very easily get an answer with power series. Okay? We know that let Sx, or this capital Fx, equal the integral from 0 to x cosine t squared dt. Okay? Notice that f of 0, the integral from 0 to 0, is 0. And by the fundamental theorem of calculus, that f prime of x equals cosine x squared. Right? The derivative of this integral function is that function back in terms of x. Okay, that's something from Calc 1 when you study the fundamental theorem of calculus. All right, so now f of x is equal to the integral from 0 to x cosine t squared dt is equal to the integral from 0 to x. Well, this has a power series representation. Minus 1 to the n over 2n factorial x to the 2n dt. T to the 2n dt. We know how to do the antiderivative of this, right? That's the sum n equals 0 to infinity. Minus 1 to the n over, so you add 1 to that, and you get 2n plus 1 times 2n factorial. X to the, or t to the 2n plus 1, evaluated from 0 to x. So this is equal to the sum n equals 0 to infinity, plugging in x for t, minus 1 to the n over 2n plus 1, 2n factorial, x to the 2n plus 1, minus, plugging in 0, you just get 0, because there's no constant term there. So this is an antiderivative right? That's an antiderivative for, or sorry, yeah, this is an antiderivative for cosine x squared. So we can get an antiderivative in terms of a power series. We can't get it in terms of any of the elementary functions that we've been looking at. I mean, we studied all those integration techniques in chapter 3, trigonometric substitutions, partial fractions, and all that jazz. But none of that would apply here. Okay, so power series gives you an answer, and it's just a polynomial. So now let's use this to estimate an actual integral. So estimate integral from 0 to, say, 1/5 cosine x squared dx with error, let's say 1/10, with error less than 10 to the minus 5th. Okay, so we'll do the same idea. So the integral from 0 to 1/10. of cosine x squared is equal to the integral from 0 to 1/10. Well, we found the power series representation for this. It's the sum n equals 0 to infinity minus 1 to the n over 2n factorial x to the 2n, which the antiderivative is equal to the sum n equals 0 to infinity minus 1 to the n over 2n factorial. I'll write a little bigger here. Two n plus 1, 2n factorial, x to the 2n plus 1 evaluated from 0 to 1/10. So this is equal to the sum n equals 0 to infinity minus 1 to the n over 2n plus 1, 2n factorial, 10 to the n, or 10 to the 2n plus 1. Ten to the 2n plus 1 minus 0, right? And this is an alternating series, which we know how to estimate. Right? It's an alternating series, which we know how to estimate. So we set up this inequality, 1 over 2n plus 1 times 2n factorial times 10 to the 2n plus 1. You want that to be less than 10 to the minus 5th. So I think just n equal to 2 will do it, because this will be 10 to the 5th right here. So n equal to 2 works. It works by a lot, actually. This would be 4 factorial. So we're actually going to get a lot more than 4 decimal, not a lot more, a little bit more than 4 decimal places of accuracy. We'll actually get 5. N equal to 2 works. So the integral from 0 to 1/10 of cosine x squared is approximately the sum n equals 0 to 1. The first partial sum as an estimate. Sum, right, because n equal to 2 works in this inequality, so use the partial sum 1 less than that. So at 0, well, it's minus 1 to the n over 2n plus 1, 2n factorial, 10 to the 2n plus 1. Which is equal to, so at n equal to 0, this is all just, well, this is 1/10. Right, this is 1, this is 1, this is 1/10. And then for n equal to 1, you're going to have minus 1 over 3 times 4 factorial, or 2 factorial, 3 times 2 times 10 to the third is 1,000. So this is equal to 1/10 minus 1 over 6,000, which is equal to 1 divided by 10 minus 1 divided by 6,000, 0.099833. So since our error is less than 10 to the minus 5th, we get 4 decimal places of accuracy, because this isn't 99 here. So this is the answer with 4 decimal place accuracy. Okay? So we can do integrals or antiderivatives of functions in terms of power series. In particular, those functions that we don't know how to do the antiderivatives of using the techniques from chapter 3. Right? Power series opens up a whole new avenue for solutions here. And then sometimes these integrals turn into series that you know how to estimate, like an alternating series, and we did just that. Okay, so that is all for section 6.4, and we will meet later today to discuss problems.